Crap. Anyway, I'm recording starting now. Good Lord. Well, thank God everyone's here. Okay. So the field stop, can you find the field stop? Which one do you find first? The aperture stop. Can you find the field stop if you don't have the aperture stop? No, you can't, because the chief ray goes through the center of the aperture stop. So if you don't have the aperture stop, you can't work. So the first thing to find is the aperture stop in your system. Then as you move away from the axis, at some point it gets blocked, okay? Typically, in a well-designed system, what will block the chief ray off axis will be the camera or the detector or the thing that detects the light, because if that's not the case, here that means if we reach the limit, the light will go, the amount of light will just go to the edge of the detector, and at some point will just stop because the detector stops. If we have a situation where the beam is blocked before, okay, before, so if I have my aperture stop, again, right here, and as I'm looking for my field stop in my system, I move off axis, off axis, off axis, and at some point, I get blocked before I reach the detector. We need to discuss this. That's where the physics is, and I know that when I teach this to undergrads, engineers, and physicists, this is not understood, okay? So what happens if I block the beam before, right here, okay? So let's assume here there is some aperture, and it blocks the beam before I reach my detector. Does that mean that here, if I were to, well, let's say on my detector here, okay, I'm trying to draw it, here, will there be light here just beyond this point? Will there be light?
No.
No?
Ideally, no, but in the real system, I think there will be.
There will be? So we have a yes and a no.
Well, yeah, I kind of agree with Elahe.
And why will there be light? Because the ray here is blocked. So how can there be light here? Help me. How can there be light?
You are just plotting the rays that are passing through the middle of the aperture stop. But if you consider all the rays with different angles, I guess there will be light.
Exactly. Okay, that's very important, because we have, what I'm drawing here is the chief ray, but there are tons of other rays. There are tons of other rays from this point here. There's the chief ray here, but there are others that go like this, and they're not blocked. They're not blocked. We need to go pretty far before they get blocked. Okay, so the chief ray is blocked here, but these rays here are not blocked. Like this. So just at this point here, how much light am I going to have at the position here where at the limit before it's blocked? What's the value of the intensity here? Because I'm drawing all of the rays originating from here. So all of the rays, if I say, let's say I have a computer program and I draw 100 rays. So let's assume I have 100 rays and I'll just make them go in all directions. So if I draw all my rays and I lose, how many rays am I going to lose if I spread them evenly as a function of angles here? What am I going to get? How many rays are going to reach the point here? If my chief ray goes here and is blocked at this unfortunate field stop, Well, half of the rays that are above will go through, and half of the rays that are below, the rays above will go through, and the rays below will not go through. Oops, I need power. Okay, just a sec. I'm almost out of power on my computer. Okay, so if half of the rays are going through, then the intensity is going to be half of what it could be. Okay, so anything that goes above here, rays that are going above will go through, but rays that are blocked by the field stop will not go through. So that means only half of my rays are going through. The intensity will not be 0. It's going to be just at this limit here. Okay, the power is going to be 50%. So I will have, say, an intensity that's high, and then when I reach the point here, I'm going to be at 50%, and then eventually 0. So the chief ray that's blocked by is the sound okay for everyone? I hear chuck, chuck, chuck. It's okay? Okay.
Yes.
Okay, so when the field stop is not at the image plane, then the last chief ray will have an intensity of 50% because half of the rays that are going to be below are going to be blocked and half of the rays above are going to go through. Okay, so the reason why I'm discussing this is that people tend to forget that the chief ray is just one of the many rays. Okay, there are many rays arising from this point here. So it's not like if nothing will go through. Okay, so we always draw the chief ray, even if we could draw tons of other rays. Okay, I could do whatever I want if I want to get the limit here. If I want to reach the point here, I could draw any other points, that any other ray that start above if they make it here. But it's simpler to take the chief ray. Okay, and I know that a lot of people don't appreciate the chief ray is one of the many rays. Okay, all right. Why is that important? Okay, when we're looking for the field of view of a system, we really need to draw this system, draw the optical system, get the aperture stop, and then just move up, 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 up until we reach this point. Sometimes, okay, and now I'll look at everyone in my lab, including myself and Valérie. But sometimes when we have the field stop in the wrong position in our systems, we'll say eliminate, and we'll get an amount of light that is not covering the whole object that we're trying to eliminate. What does that mean? That means we have a limiting aperture for our light source that is blocked and prevents us from imaging or eliminating everything in our system. Okay, so the other thing that happens very often when people draw design their own little microscopes is that they'll take a camera, they'll put it in their system, and then you'll see, say, just the central part will have a nice image and it's going to be black on the sides. What does that mean? That means that there's something elsewhere in the system that is blocking the chief ray off axis. So if you analyze your system, then you'll find that you may have a lens that's too small. You may have a filter that's too small. You have something somewhere in your system that is blocking the chief ray off axis and therefore blocking the field of view. And just nomenclature, just to be sure that we understand all the words. The field of view is defined for the object. So we'll say, I have a field of, let's say if we use a camera, you know, let's say a camera, we'll say, oh, at 10 meters, I have a field of view of say 3 meters. So it's in object space, so it's big. On the other side, the field of view is an object concept. And on the image side, we just call that the image size. Okay, so image size is in image space, field of view is in the object space. Okay, again, how do we find this? Yeah, wait a minute. I'm losing my slide. Where's my slide? Give me my slide. Slide. Yes. Okay. So in an arbitrary system, how do we get this field stop? Well, we don't need to know. This one is simpler because again, we go on the object. We have the aperture stop because we can't do anything without the aperture stop. And then we move up, up, up. We always get the chief ray. And then at some point, the chief ray is going to be blocked. And we call that, the thing that blocks it is called the field stop. And the position on the object defines, so at some point, the chief ray is blocked by the field stop. So that point defines the
field of view.
Field of view, or half the field of view.
Yeah.
Good. Just factor of 2. It's just a matter of definition. Okay. In the ray tracing program that I gave you, all of that is performed for any system because it's once we have ABCD matrices for a system, the procedure for finding the aperture stop and the field stop is straightforward. It's just an algorithm. We don't need to know where the lenses are, etc. The thing that's the most interesting is how we find the image of the aperture stop and the image of the field stop. So I told you the image of the aperture stop is the entrance pupil and exit pupil. We have the same thing for the field stop. The field stop is called when we look at it from the object space, we call that the entrance window. And from when we look at it from the image plane or the image space, we call that the exit window. However, as I said before, the field stop in a well-designed system is always the camera. It's always the camera that's positioned, obviously, at the image, okay? So usually, in a good system, the field stop, the entrance window, the exit window and the field stop are the same. The entrance window is what I see from the object. So from the object, I will see, when I look at the image, I will see
Field of stop.
the field of view. I will see myself. I will see the maximum that's possible on the image. So that's the field of view. Okay. I have tons of little questions that I will give you, and you will need to go to the ray tracing program to double check everything. So there are, to become at ease with manipulating ABCD matrices, you'll need to find the general definitions for the positions of an object or an image in an arbitrary system. And I will give you various problems to find that in a general system. And you will take a look at the code also the Python code that describes all of this in the ray tracing module to confirm that you got this right. So this was a little bit longer than I expected, but it's absolutely essential for you to design. Oh, there are two things that can happen actually. Sometimes we want to design systems. Sometimes, you know, there are optical, and being an optical designer is rare. Okay? There are very few people being optical designers. They're rare, they're expensive, and they know a lot of things. So sometimes the question is not to be able to design a perfect system, but at least to recognize that your system is not perfect. And then you can go to an optical designer and say, I have this particular problem, and then they can fix it for you. I do that myself. The company that I work with, Blick Photonics, does that. We're not optical designers, but we'll get this approximately right and say, oh crap, what is this? You know, we have an aberration, or we have this certain problem. We'll just give a contract to someone who knows the details, but a very, very specific contract. So with this, you can probably fix your own little system. And if the system is too complicated, you can at least appreciate that something is wrong and get it fixed. Okay, so that was my goal with this, all of these diaphragms, apertures, and other problems. So, unless you have questions, anyone has questions? Was it too fast? Well, you'll have an assignment to catch up if this was too fast. We'll take a break, and then we'll just go for an hour after that on a different subject. So, is that okay?
Good.
Yeah.
Okay, so let's say let's come back in approximately 5 minutes, maybe a bit more. Okay.
Have you tried to install the ray tracing program?
I tried, but I couldn't.
Yeah, same. It didn't work.
Yeah.
I thought about reinstalling all of my programs. Perhaps that's the reason, but since for you it's not working as well.
Maybe I just thought that because I don't know anything about Python, maybe there was a problem with that. But Ella, did you try the ray tracing program on Python?
Not yet.
Could you please try it and tell us if it is working or not?
Sure. Oui, ça marche-tu?
Yeah.
Thank you.
I think it's my computer, the problem. What is it?
What's the problem?
Well, that's what I'll open Python, try. I don't remember what is the code thing or whatever.
Hola. Sorry.
We were saying that the ray tracing program doesn't work. Well, for me and Shadi, it doesn't work. But I don't remember what kind of.
Okay.
I don't remember what is the problem exactly. Okay. I think it's Anaconda. Well, my problem is Anaconda.
Yeah, I guess so.
Yeah.
Yes.
Yeah, I think it. But well, yeah, I'll just reinstall everything, and if it doesn't work, I'll send you a text or something.
Okay. Well, on your Mac, just to make sure, if you want to confirm that everything is fine, okay, you install Anaconda, and I'm assuming you then open a terminal like this to start. Ideally, you'd want to type Python to confirm that everything is fine. Okay. Look at
just type Python.
Yep, but you'll see. Let me show you. I'll show you an example. Okay. On this computer here. Okay. If you type Python, you see that it will say it will give you what's called a prompt, a Python prompt. There's always one that's installed by default on the Mac. And this, do you see that on the computer here, it says that it's Python 2.7. You have to type which Python, like this. You see this? Which Python? And if it says user bin Python, that's because you're using the version that comes with the system, and that's not the right one. Because if you type Python -- version, It says Python 2.7.16, which is not right. The ray tracing program will not work with Python 2. You need to have at least Python 3.5. So if you have it installed properly, so now I did that without you noticing it, but now I'm on a different computer, okay? I was connected to a different computer before. So on this computer, okay, I'm not on the same computer as before. Now, if I type which Python, you see that it says user DC Cote Anaconda bin Python.
Yeah, that's what it tells me also.
That's what it says?
Yeah.
Okay, and if you type pip install pip install ray tracing like this.
I don't know, just a bunch of stuff appear.
You can also type Python ray tracing upgrade. So then to make sure that it works, you type Python -m ray tracing, and then you'll see the examples. So that must work.
Yeah, I install ray tracing, but when I write a --update, upgrade, sorry, upgrade. Yeah, upgrade. No such file or directory. But I'm sure I installed it. Anyway.
No, it's important. It's important. So if you type, if you type pip install ray tracing, it says pip not found.
Yeah.
Okay. So maybe pip is a separate program from Python. So if you don't have pip, then you have to get pip. And everyone sees my computer, right? No. Okay, if you go on PyPy, ray tracing, okay, ta-da! So it's right here, okay? If you don't have pip, you have to get pip, okay? So there's, do you see this here? There's a program called get pip. So then you keep this link, you download it. If you click on it, it will download it, or obviously it's not downloading. You have to click download linked file. Okay, so now it has downloaded the file getpip.py in your download folder. You see that?
Yes.
Valérie?
Yeah.
Okay, so then if you go to your download folder, everyone sees what I have, right? Like this. Okay. So now in my download folder, there's a file called getpip. It's right here. So if you type Python getpip, it will get pip and install pip. So now it's installed. See, it says successfully installed. So now you have absolutely everything if you didn't have pip before.
I'm pretty sure it worked. How do I know if I have retracing or not?
You type Python -m ray tracing.
Okay.
If that doesn't work, then you should see a small window that opens with a drawing, like.
No, it works.
It works?
Yeah, it works.
Okay, good. Ta-da! Awesome.
But it's just when I want to use it with, I want to like to code my own stuff, that doesn't work.
Okay. Well, when you code your own stuff, the first thing you have to do in your text. Okay. Let's say if you want to, everyone sees my computer again. So the first thing you have to do is import ray tracing like this, right?
Yeah.
Call it test biophotonics. So if you type ray tracing like this, then you'll have to refer to everything in the package with ray tracing dot matrix, for instance. And that gets annoying. So you can do from ray tracing import star like this, and then you don't have to write ray tracing before. No? Does that ring a bell to everyone? No?
Yeah.
I'm looking for, yeah, okay. I'll find an example. Yeah, we'll take this one. There you go. So you can do path, optical path like this, path dot append lens f is equal 10, etc., etc. So that should work, right? Anyone has used the ray tracing package? No? Shame on you. Yeah, you, who has?
Yeah, I did.
Okay, good. Woo!
I used it before, but now it doesn't work on my computer.
But now it's, so if you type, okay. Let's just, one last thing before we stop. Let me just delete all of this. This is slightly annoying.
Yeah, it's just a problem with the software I'm using.
But
like
if
PyCharm doesn't know where Python is.
Ah, okay, so that's different. Anyone has used PyCharm?
But it's fine. I'll be able to find a solution for that. I think so.
Yeah, we're done. That's fine. But I'll show you where it is. In your preferences, you have to say, it's coming. You have to say in your preferences that the tools, Python integrated tools, where is it? Well, somewhere you say, use this Python. Where is, I can't find it, but somewhere you're gonna say, my Python is here. I guess it's gonna be here. Yeah, the project interpreter. So see that mine says Anaconda 3 Python, Python 3. And if you don't do anything, it's gonna use this. It's gonna use system Python, and that's not gonna work. So you go in project interpreter. Done. Okay. Okay.
Thanks. I'll try that.
You will have, there's a lot of documentation for the package. And the most important part really is that you will have to take a look at the code, and sometimes it may get complicated if you don't have, if you don't know where the code is on your computer. So if you need the code, go directly on GitHub, which is what I'm trying to do now. But for some reason, okay, there you go. So all of the code is here, and all of the details, all of the Python and ABCD matrices. If you go to matrix.py, you'll have all of the code and everything is commented. Why am I discussing this now? Why does it look like I'm wasting my time discussing this? That's because I want you to be able to go, say, into, if you go to imaging path, an imaging path is a collection of matrices, you'll see that there's something called a chief ray. marginal rays, even aperture stop. So all of the functions are defined here, and you have all of the details, and you'll be able to confirm whether or not you got the math right in your assignment. Okay, field stop. Woo! Field of view is the next one. There you go. Everything is here, everything is commented. Image size. Okay, and you'll see the code is very simple to understand. Okay, good. All right, so I hope this is sufficient, because that's it for the part on the diaphragms, and we have only, yeah, this is done, this is done, this is done. Yes. Okay. So if you don't have, all the other questions that are relevant will be in the assignment. I don't want to go through. I want you to go to the gym, make muscles by really doing real problems in the next assignment. Okay, so yeah, okay, now I need to go to share this. You should see my iPad in a second. There we go. Okay, so the second part, we have looked at the optical components. Okay, so we have discussed where we put the lenses to make an imaging system, and I gave you the most basic. I told you the tiny little details that we needed to make a scanning system. Okay, so you'll have enough for the assignment. Okay, so where to put a mirror and how do you need to scan, etc. Okay, that part you'll have questions in the assignment. But in the end, we have discussed detection last time. Okay, we have discussed on the previous course, previous lecture, we discussed the detectors, the CCDs, CMOS, PMTs, etc. But eventually, because we're doing imaging, we'll end up with an image. Okay, so this is not important here. Okay, so eventually we make either some sort of a 4F system. Okay, we make. Just a second. Okay. Oh, my pen has no more batteries. Uh-oh. Okay, I can't draw anymore on my. Oh, that's a bummer. Okay, we can make a 4F system, and in this 4F system, we'll have an image, we'll have an object, we'll have an image, and we'll create the image at the camera, or we can sweep a laser beam and reconstruct the beam, reconstruct the image sequentially. These are the two types of imaging systems that we can make, and you have questions in the assignment regarding that. But that's the optical part. Now, what we really want to do is when we digitize the image, we end up with some sort of an image. So how do we store it? What do we do? What are the details related to the creation of that image and the management of that image? Okay, so today we'll discuss, for the next 20 minutes, I'll set the table so we can discuss bit depth, resolution in pixels, compression algorithms, and various other things like that. Okay, so yeah, in all cases, we end up with a representation of what's at the image plane, either from a scan system or from a camera. If If I put a camera at the system, okay, let's say if I have an imaging system if I have an imaging system like this, okay, whoops. Okay, if I have an object and an image, the camera that I put here, okay, will limit my field of view, that we know, but it has small pixels, okay? It has small pixels. How do I know what the resolution of my image will be? So there's all the optical details, okay? I send my beam into my optical system, and at some point I put a CCD, a CMOS, something, a camera. So how do I know the resolution of my system? What are the things that I need to consider to get the resolution of my system? Nope.
There are a lot of things. For example, the aperture stop can change the resolution.
Mm-hmm.
Also, it depends on the objective you're using. Well, which lenses.
And
like what, the NA and stuff.
The NA, okay. The NA, good. Mm-hmm. Anything else? So if I have an objective that has a very large NA, okay, so we know that the NA is the inverse of the F number. So the F number gives the resolution. The NA also gives the resolution. So if I have a certain objective with a certain NA, do I know for sure what the resolution is going to be, or there's something else?
It will depend also on the pixel size that you're using for your camera.
Size. Yeah. Exactly. Because when we measure the image, there's always a point where we take the actual image or the light on the image and we digitize it. So when we digitize the image, we have to make a decision. We have to say, well, I will just assume that the light that's in this square, I will replace all of the light in this square by one number. And a camera has pixels like this that are separated by that are a certain size and separated by a certain distance. There's a little bit of dead space between the pixels here. So I may have a certain resolution with my objective, but the camera will always, not always, no. The camera will be a factor that needs to be looked at. In a commercial system, that's usually not something we have to worry about. In a commercial system, they have their own objectives and they will support a certain camera. So it will always be that the objective is the limiting factor for the resolution in a commercial system. You buy an Olympus system, an Olympus microscope, a Zeiss microscope, and you only use Olympus objectives and Zeiss objectives in the Zeiss microscope, you'll be fine. But we do make our own microscopes very often. Most people here will tweak and change cameras and try things. So then you have to look at the pixel size of your camera when you put it in your system, okay? So, and I say this because we keep changing. Very often we find a new camera and the supervisor is going to say, oh, this camera is so much more sensitive. We should really use it. And we'll just assume that everything is going to be fine. Well, not necessarily. It may be more sensitive, but maybe the pixels are not the same size as the pixels of the original camera in the system. Okay, so this is something that you need to appreciate, that in a perfectly designed system by someone else, if they know what they're doing, they did it right. But we always exchange components, or we take an objective from Olympus and we put it on a Zeiss microscope. You know, we do that all the time, okay? Because we'll say, oh, this one is better, okay? But as the biophotonics person in the group, you need to know the details. So for the cameras in particular, we will worry about the size of the pixels, and especially for cameras, we will really worry about what's called the bit depth, the dynamic range, and the well depth. And they're all different concepts that we need to discuss now. Okay, so yeah, okay. So as I said before, the pixel size may not give the resolution of the image. The resolution of the image is given by the diffraction of the spot in the objective, and that we know, right? We know that there is an expression that I discussed last time, I think, unless I'm mistaken, but the resolution is 1.22 lambda divided by NA, unless I'm wrong, okay? So this is the size of the diffraction spot at the center of the pixel. Usually this will be bigger than the pixels. If it's bigger than the pixels, that means the optical limit is the real limitation in the system. And if the pixels are smaller, that's fine. The resolution of the image is not given by the size of the pixel, it's limited by the optical components, okay? All right, so when we buy cameras, especially now, there's so much development in cameras that the pixel size, pixel sizes will change, okay? There are various sizes of pixels, 25, 13, 8, and even you can now buy 2 micron pixels, cameras that have a 2 micron pixel size. So all of this you really need to know. So when you pick a camera, you need to know, you will need to know the pixel size, because for instance, if you, I'll go back to my other slide. So if you buy a camera and you say, oh, I have this Orca Flash Hamamatsu. It's 2048 by 2048, and the pixel size is 6 microns. Okay. Oh, I have this other camera, and it's also 2000 by 2000, but it goes, say, at 10,000 frames per second. I really want to use this one. Well, it's possible that the pixel size may be 4 times as large, and all of a sudden your camera will just have a sensor that's 4 times as large, and you put it in your system and it's not going to work, because most of your sensor you're not going to be using, because it's bigger than the image size for the design system. Okay, so figuring out knowing the pixel size is important, because it will give you the size of the sensor. And the size of the sensor you do want to match in your system. If you're replacing a camera from another system, you want to have the same, you really want to have the same sensor size to make sure that it is in your system, the field stop. The field stop should be the sensor size. So if you change the camera, you want to have the same sensor size. Okay. Okay, sorry, someone was using the microwave in the house. Okay, so if the pixel size is 8, 13, or 25 microns, that's the size of the pixel. But the pixel is in the image space, and the object is, let's say, 20, 40, 100 times smaller than what we have in the image space. So when we have an objective that's a 40x, then if a camera has a pixel size of 25 microns and it's, let's say, a 50x, then that means the resolution in object space will be half a micron. Okay, so the pixel size is always given by in image space, but we care about the resolution in object space. When we describe the resolution, it's always in object space. Okay. Yeah, blah 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 blah. Yeah, that's fine. Okay, so my flow is not the flow of my original slides. I just gave this equation before. Okay, the resolution is 1.22 times lambda divided by NA. That's the optical resolution, and the final resolution will be the largest of the two. Is it the optical resolution or the pixel size? In a good system, it's always going to be the optical resolution that's the most limiting factor. That's the way it should be designed. Okay, so yeah, the worst of the two is the resolution of the system. Okay. One final thing for CCDs, and that'll be it for today. This is, if I say the word bit, okay, if we talk about bits, anyone can define, when we say it's an 8-bit image or a 12-bit image or a 16-bit image, what do we mean, really? What do we mean? Why do we talk in terms of bit, and why does it matter? When I say an 8-bit image, what does that mean?
It means that we can have the image in, we can have 2 power 8 different values for the image.
Exactly. At each pixel, okay, an 8-bit image is an image that, okay, a bit is 0 or 1, and if we combine, I'm going to try to draw it here, but if we combine, yes, so if we combine 0, 1, 2, 3, 4, 5, 6, and 7, if we combine 8 bits together, okay, if we combine 8 bits together, which I had just drawn, but they're gone, okay, we will get all the values that this can take will be 2 to the 8. So an image, an 8-bit image, each pixel can take values from 0 all the way up to 2 to the 8 minus 1. So that's 255. So in total, it has 256 values. Why do we care about that number? If you are trying, okay, if you are trying to measure, say, the calcium activity of cells, when we measure the calcium activity of cells, we have the fluorescence. We have fluorescence all the time. And then when there's an influx of calcium, the fluorescence is going to go up a little bit and then back down. So if you only have 256 possible values for each pixel in your camera, let's say if it goes up just a little tiny bit, well, maybe it may go from 128 to a fraction of a bit. So maybe you will not see that difference, okay? So the number of bits you have will limit how small of a change you can see, because if you're at 128, you need to see a change when it reaches 129 or 130 or 131. So the number of bits will limit the resolution, how small of a change you can see. And now you may be thinking, okay, I don't see, you know, it's 0 to 256, but what's the connection with the actual camera? Okay, if I have a camera, we discussed last week that in a CCD camera or a CMOS camera, we have photoelectrons that are hitting each pixel, and an electron is generated each time a photon hits the camera, and then we count the electrons. Well, when we digitize the values in a CCD camera, it's not like if the pixel is limited to 256 electrons. Each pixel has a well depth, and that's a physical property of the sensor. So let's assume, like the Orca Flash, for instance, that the pixel can contain 300,000 electrons. So we say the well depth of this camera is 300,000. So if I'm digitizing this as an 8-bit value, that means, okay, just for simplicity, I will just, okay, it's only for simplicity. I'll say that it is 255,000. The well depth is 255,000. Okay, so that means that if I get just one photon that creates one electron, I will have one electron. And when I digitize that in 255 different values, then it's going to be 1 out of 255. But if I'm digitizing this as 8 bits, I need 1,000 electrons to get 1, and 2,000 electrons to get 2, etc. So I will only get a value of 1 in my pixel once I have reached 1,000 electrons. And it's, even if it goes up to 1,500 electrons, I will not see, well, or 1,400 electrons, I will not see 2. I'll see 2 when I reach 2,000 electrons. So the well depth is important, because if I have a certain well depth and a certain bit depth, I will know how small of a change I can see in light. Okay, this is important. Okay, this is very important, actually. So if I'm trying to see, if I have a very small amount of light and I'm trying to see a very small change, it's possible that with, say, an 8-bit camera like this, I will not be able to see anything. Let me give you an example. Let's assume that I have a small amount of light and I get approximately 5,000 photons per exposure time. So if I have 5,000 photons that are hitting this pixel per exposure time, I'll get approximately 5,000 electrons. And once I digitize this in 8 bits, then I'll have the value 5 in my pixel. Well, let's assume that the intensity changes by 10%. Many calcium indicators have a change of 10% when you, from the baseline, when there's a calcium influx. It may change by 10% or 20%. Let's just take 10% for now. So the amount of light will go up by 10%. Well, 5,000 photons times 10%, that it's going to go up to 5,500 or 5,500. Am I going to see a difference on my camera? Absolutely nothing. Okay, I will not see anything. And that doesn't mean that the camera cannot see a change in 10%. No, it cannot see a change in 10% when you only have 5,000 photons per exposure time. But let's say I have 50,000 photons per exposure time. And now it goes up by 10%. Well, the value in my pixel is going to go from 50,000 photons digitized in 8 bits will give me a value of 50. And if it goes up by 10%, it's going to go up to 55,000 photons or 55,000 electrons. And therefore, the value will go to 55 once it's digitized. So the amount of bits and the well depth will give you the resolution in photons that you can see. If the value is too small, you may not be able to see the change you're trying to see. Okay? So that's one, you have to choose the right camera. The second thing is sometimes I've seen that several times, that people will say, oh, my images, they're very big. It's taking too much space on my USB key. I'll just convert that to a JPEG, or I'll convert that to an 8-bit TIFF, for instance. Well, sometimes you will just destroy your data if you go from 16 bits to 8 bits. Okay, so there are image formats, and that we'll discuss next time. I think right now is not the time to start that, but the bit depth of the camera is something you start with. But then as you manage your images, you may say, oh, I'll save this as a TIFF or a JPEG, etc. Oh, you may destroy the information, and it may render your data completely useless if you don't do it right. The opposite is also true. I've seen other groups, not my group, I've seen other groups acquire big 16-bit images just to see where the cells are. So you don't really need to have, unless, for instance, you're trying to do calcium imaging, you don't need to have 16 bits of resolution just to see cells moving across your sample. 8 bits is sufficient. So then all of their data was gigabytes and gigabytes of data, 16 bits, 3 colors, whereas they only needed 1 color in 8 bits. So managing your data properly will have an impact. Let's say if you keep a 3-color image, an RGB image in 16 bits, whereas an 8-bit image, single color was sufficient. Well, treating that data will take 8 times more time if you keep everything that's useless, whereas if you keep it as grayscale in 8 bits, it's going to go 8 times as fast. Well, that's the difference between 10 minutes and an hour. So that we'll discuss next time. So the reason why I wanted to discuss this first is that this was the last connection with optics and hardware. Okay, so we with the CCD, okay, there's a link, there's an interface there. We have optics, we do stuff with real physical quantities. Then the camera is between us and the computer, and the camera will dictate a certain bit depth, a certain resolution, etc. After that, when we start managing the images, then we have to be careful. Okay, so that's gonna be it for today, because we're going to deal with images and the details of images next time. But I think right now is a good moment. I would have liked to go further, but I was too slow with the first part this morning. So do you have questions? No?
Nope.
Okay, I will have a fairly sizable assignment for you that I will send you hopefully today. And then when's a good time for the next lecture? Then is it the next final lecture? Yeah, I think it's, yeah, have we had 3 or 4? Was that number 4 today?
Yeah.
Yes.
Yeah.
Okay, so when's the next one? Is it Thursday or Friday?
Whenever.
Friday is better for me.
Okay, Friday. Oh yeah. Yeah, Friday is much better for me too. Not in the morning though. I'm teaching optics in the morning. So how about 1 in the afternoon? Is that too late on a Friday?
All right.
All right.
No, it's okay.
Okay.
Anthony,
Yeah.
we have Theresa's practice on Friday at 1 p.m. You think we should?
Ah, ok, ben on peut.
Oh, I didn't know that.
Yeah, they just sent an email to say that it was bumped to 1 p.m.
Okay.
I'll just make sure that it's this Friday. Yeah, this Friday.
So we could also do 11, but then we'll have to go through lunch. Even 11, it's at 1? Your thing's at 1?
Yes.
Well, I guess we could do 10:30, but I may be a bit late because I'm teaching 8:30 to 10:30. And next Tuesday is the exam, so maybe students will have questions.
But is it long what you have in the afternoon? Because if it's 1 hour, we could start at 2. If it's okay for everyone.
Well, Paul said it was from 1 to 3 p.m.
Okay.
So, but I don't know if it will take all that time, but I can't know.
So what about the Thursday?
Yeah, what about Thursday?
Yeah.
Thursday, I'm all free.
Okay, but so you won't have tons of time for the assignment, so I'll make sure that I send you the assignment by the end of the afternoon.
Perfect.
Okay.
All right.
So, okay, so if you have, I'll send an email to everyone with reading, a link to the slides, a link to the video. Unfortunately, the first hour is going to be missing. And any other documentation that you guys see fit. And please take a look at the ray tracing. I'll give you a link to how to install ray tracing on your computer. If you have problems, just send emails to everyone so we can all see the replies, just in case everyone has the same problems. And I would really like to have everyone with an operational ray tracing module on your computer. Okay?
Okay. So good. Thursday at what hour?
I think that I seem to have a meeting from 1 to 2:30, but I'm not sure. I don't know if I have to be at that meeting. So we'll just assume, I'll say 2:30. Let's do 2:30 to 5. Oh, good Lord. 2:30 to 5, okay? 2:30 to 5, and then that'll be it. Okay?
Okay.
Good.
Is that good? Is that good for everyone? Shadi?
Yes.
Okay.
Yes. Yeah.
Yeah.
Okay. Good. If there's anything, let's just go through email and reply to all, so everyone stays in the loop. Okay.
Okay.
Thank you.
Have a good day.
Thank you.
Bye-bye. Thank you.
Bye.